Imagine that you and your friends have created a startup company that is focused on creating a better coffee machine, one which has a steam wand which will more effectively froth the milk. Let's look at the simplified geometry here of that steam wand. We have steam in this pipe passing through here in the center. This is the area which is shown in red. That steam is condensing on the wall, keeping that wall at a temperature of 100 degrees centigrade. That central steam pipe has a radius r⁻1 and a wall temperature of T⁻1. This steam pipe is surrounded on all sides by insulation, which you can see here and here. This insulation has an outer radius of r⁻2 and an outer temperature of T⁻2. So the formal statement in the problem is that we want to find the temperature distribution, T of R, in the pipe insulation, subject to temperatures T⁻1 and T⁻2. We will then sketch the profile and compare this to the planar insulation case. We will also compare the heat flux and current at both r⁻1 and r⁻2. The assumptions that we'll apply here are that we are at steady state. There are no time variations in this problem. We have radial symmetry, so there's no angular dependence. The system is invariant in Z, meaning that the beginning and the end of the pipe don't create any sort of edge effects in the system. We have a constant thermal conductivity, K, and there is no generation of heat in the system itself. So Q dot gen is 0. So we're going to begin by establishing a simplified governing equation. We have the full equation written out here in cylindrical coordinates, which we introduced just a moment ago. We can eliminate one term due to radial symmetry, another because the system is invariant in X, and because there's no generation, get rid of yet another term, and because we're in steady state, cross out the term on the other side of the equal sign. And this leaves us with just one term. We can integrate this, and we get that the temperature equals A times the natural log of R plus B. We have two constants, A and B, that we want to solve for here. We need to apply boundary conditions. That the temperature at r⁻1 equals T⁻1, and the temperature at r⁻2 equals T⁻2. If we take these boundary conditions and we apply them to the expression just above them, we'll get our temperature distribution. The best way to visualize this temperature profile is to plot it. So let's sketch this profile and also compare it to the case of planar insulation, where if we had a temperature T1 on one side and T2 on the other side of a planar slab, what that profile would look like. So we start out with our axes on which we've marked R1 and R2, as well as the temperatures T1 and T2. You'll notice that T1 is higher up on this axis since we are assuming that the steam is warm relative to the surroundings, which are at T2. We plot these points that we have temperature T1 at R1 and T2 at R2. And now we can plot our solution. This is the solution that we showed just a moment ago. And you'll see here that this is curved. If you can't see this immediately just by looking at the equation, that's okay. You can plot it in MATLAB and use that to help build your intuition for what different equations look like. We can compare this to the case of planar insulation. So let's assume, like I mentioned just a moment ago, that we have a temperature T1 on one side of the slab and T2 on the other side of the planar slab, and we can look at what that will look like. What we would have in that situation is just a line connecting these 2 points. So we can see very clearly here the impact of the fact that we are in cylindrical coordinates. That this temperature distribution goes from being linear in the planar case to being curved in the cylindrical coordinates case. Let's consider now the heat flux in this system. We know the equation that tells us the heat flux, that it's Q sub R double prime equals minus K dt dr. This is the heat flux in the R direction because the heat is moving in the radial direction. We can apply this at both R1 and at R2. And we can see on this plot up top what this looks like. So it's the gradient here, which is controlling of the magnitude of the radial heat flux. At R sub 1, the heat flux is larger because there is a steeper gradient there. While at R2, we have a smaller slope, and hence the heat flux will also be smaller. We can write this out in mathematical form that Q sub R double prime at R equals R sub 1 must be greater than Q sub R double prime at R equals R2. We know, however, that if we were to multiply the flux by the cross-sectional area, that the heat current that results must be the same. This is just another way of saying that whatever heat crosses the boundary at R sub 1 must then cross the boundary at R sub 2 because we are at steady state. So if we take the flux at R equals R1 and multiply it times the cross-sectional area at that point, which we will refer to as A sub 1, we can set that then equal to the heat flux at R sub 2 times the cross-sectional area at radius 2, which is A sub 2. This is just enforcing the heat balance. We recognize, of course, as we've mentioned in words, that Q sub R double prime times the cross-sectional area is simply a heat current. And so we can write that out in mathematical form, that Q sub R at R sub 1 equals Q sub R at R sub 2. Again, that whatever heat current crosses the boundary at radius 1 must then cross the boundary at radius 2.